Well, hello, everybody, and welcome to the next in our ongoing series of year-round panels brought to you by the SIGGRAPH Pioneers. I am Ed Kramer. I'm chair of the Pioneers Group, and you're going to be in for a real treat tonight. We have some amazing guests here to talk about the subject of chasing pixels, the pioneering computer graphics processors. Before we get going with that, Jon Peddie is going to lead that, and I'll introduce Jon in a moment. But I first want to give the floor to Bonnie Mitchell and Jan Searleman, who have been doing a tremendous job organizing the SIGGRAPH History project, and they're going to let you know a little bit about that. So take it away, Bonnie.
Okay. We want to let you know about a couple of very important, exciting projects that the History Committee is doing. And one of the things is an online archive of everything SIGGRAPH. And so we're going to make this real quick. We encourage you to go check it out. We'll put the link in the chat. But first of all, it's an online archive, and we've been working on it for about a year. It's not done, but it's coming along really well. And on the front page, you can see the updates of what we've added to it and what clearly needs to be added. So we have publications and animations and courses and all kinds of fun things. So for instance, we're almost done with the courses. We're working in the 80s. Pete actually, one of the speakers today, is helping us with some of the problems and missing information in the 80s. And then we have to dig through the 70s. That's going to be a challenge. And then we have lots of animations. We have about 1,400 animations, not animations really, just documentation of the work. So just basic information about it. We also have lots of panels that you can view by year, or you can view them all. We have hundreds and hundreds of panels, and we're working again in the 80s now. We went backwards on those. And so if you take a look at them, you can scroll down and look at them in lots of different ways. Please explore. We have all of the art from the art shows already entered. Except for some of the early stuff is missing. If you ever see this, image not available, please help us out. We have Appy Hour, quite a few Appy Hours. We just have 2021 to add. And we have art papers and presentations. All of them are added. And we have all of the awards. Now we are missing some pictures, and I know some of you guys might be out there. Or know somebody that's out there. And Jan's going to tell you a little bit about the most exciting part of the online archive.
Sure. One of the fun things, of course, is the collectibles, the memorabilia, the shirts, the mugs, the pins. And so we have started to accrue quite a lot of those and getting those images. Anyone who knows any information about them. For instance, I met the designer of this 2007 shirt. It'd be really cool if we could get his name, for example. And so that's an ongoing project that you can look through and have fun and remember the experiences we had at SIGGRAPH.
And Jan's going to talk about sponsorship as well.
So this is one of the newer things, and thanks for all those wonderful teapots and Stanford bunnies and all of those things. We're looking for contributors to help us have this, create this project. It's a very large project, and particularly we've had some funding. Thank you to SIGGRAPH History Committee and to the ACM History Committee to pay some students, but we really could use a lot more student help, and we want to pay them both for adding this information or taking care of the images and getting it into the archives, but also seeing if we could sponsor students to actually attend a SIGGRAPH and have the experience for themselves.
Our newest thing is we have started the SIGGRAPH physical collection of items. Bowling Green State University, home of the second conference, SIGGRAPH conference, has given us an office and lots of bookshelves. And so we have started the SIGGRAPH physical collection. We're looking for 2 copies of everything. The University of Waterloo got us started, and they gave us their entire collection. Mary Whitten had quite a collection of materials. Jim Foley donated materials, lots of other people as well. And my huge collection, I am definitely a hoarder. And so I used to be until I gave it to this collection. And so we're organizing it and we're making inventories right now. This is just started like last week. And I went up to Canada, got the materials. And this week I started making inventories. So at the bottom of the master collection page, you can see the inventories. And if you look at the inventory, you're thinking, I want to get rid of those boxes in my basement. Take a look at what we have, contact me, the email's right on the page, and let's talk. And I think that's the end of my advertisement.
Yes, thanks, Ed, for giving us this chance to show it to people.
Well, my pleasure. And you know, you guys, I really think that one of the missions of the SIGGRAPH Pioneers is exactly this, to be the people who, you know, we're the ones who have the stories, we have the memories, and preserving that important heritage is really, in my mind, one of the missions. So without further ado, I would like to get our panel kicked off. So I'd like to introduce Jon Peddie, president of Jon Peddie Research. He's been chasing pixels his entire life. So Jon, take it away.
Okay. Thank you, Ed. Hi there, everybody. Thanks for attending our discussion on the pioneers of pixel graphics and processors and systems. Our host, who you've just met, film slicer, timekeeper, chair of the SIGGRAPH Pioneers, is Ed Kramer. My name, as he mentioned, is Jon Peddie, and I'll be asking our esteemed panel a few questions. I'll mostly be quiet, thankfully, but I want to know how they did it, what they did, why they did it, and point out that what you're going to be hearing tonight is an explanation as to how we got to GPUs. We kind of take GPUs for granted today. I can assure you they didn't always exist. And I know that because I just wrote a book about it, and it was no short trip. You know, it started back in the 60s, believe it or not. And we finally got to the point where we had a fully integrated GPU in the late 1990s. So that was, you know, several decades to get there. It took Moore's Law, and it took a lot of hard and creative work to get that integrated chip. That functionality would fill 2 U-rack chassis a decade or so ago. So that's an example of how we miniaturize things. One of the early adventurers who didn't know you could make a graphics processor with a bunch of TI 74 chips, he and his partner, Mary, just went and did it. And so Nick England and Mary Whitten are with us tonight. And they were probably the first GPU-like processor that got built with discrete components, and they have some stories to tell. So let me get out of the way. Nick, tell us what you and Mary did.
So my first programmable graphics processor was using something called an Adage AGT30 in the lab at North Carolina State. It's those 4 racks that are in the background of this photo. It drove a vector display, a 3D vector display, and the guys in the lab also built a color raster display. So this was sort of our state of the art in 1972, a fully functional computer which had an integrated 3D display and an auxiliary processor, a mini computer that drove a color raster display. 1972. The Adage AGT originally, the original design was in 65, and then it was upgraded in 68 but it used a hybrid array in order to do matrix multiplications, a combination of digital and analog logic, because that was the only way you could run fast enough to be able to do 3D perspective display and vector display. No CPU, no ALUs, no GPUs in there. Just a big computer, but it had the hybrid array that would do all the transformations and then display vectors. Early raster graphics systems had a processor. It typically was like 12 or 16 bits, and it was built out of that 7400 series TTL logic that John mentioned. But it's set right between the host computer, which like a PDP-11 or something like that, and the frame buffer memory, refresh memory it was called back then. And you could only do, typically, you could only do the things that it allowed you to do. You could do lines, characters, 2D polygons, but that was about it. There was one, the Genisco programmable graphics processor, and this is a block diagram. It sits right between the host and the memory, but it did have a writable control store, so you could program it to do a few things. And I think this is the machine that Henry wrote some code that would do a Z compare and conditional write. So that was the first Z buffer happening in a graphics processor that I know about. And Henry can correct me if I've got that story wrong. By 76 or so in the lab, Turner Whitted had joined us as another grad student, and he was doing curved surface displays. And this seemed to me like, well, this is the kind of graphics you'd really like to do on a graphics processor. So I got the opportunity to build a 32-bit graphics processor. It used the AMD 2900 family of what we call bit slices. Each one of these large chips is 4 bits of a computer. It made a 32-bit computer. It used a 64-bit wide instruction word. So I tried to do a lot of things at once, and to not just make a general purpose computer, but to make one that was kind of optimized for doing graphics and imaging operations. The 2900 family, that bit slice part was used in a lot of machines. This is my Battlezone arcade game. Some of you may remember this. This is probably the first 3D arcade game. The circuit board here has got 4 of these 2901 chips, and this was their math processor. So it did all the transformations and everything. SGI used it for rendering in their first systems. Later on, they did lots more, but they had the geometry engine for doing geometry, but then they used this 2900 series bit slices for actually drawing things. Yes, in a pipeline. I tried to do something that was a lot more flexible. It's not a pipeline design, but instead a bus-oriented design. Mary and I, after having several people visit the lab and say, "Oh, that's really cool, could you build me one of those?" decided to start a company. We didn't know what we were doing. You'll hear more about that later. But our mission statement and the very first thing that we handed out at SIGGRAPH 78 was we would strive to meet the graphics requirements of advanced research groups. That's not a good business plan, folks, but that's what we did. So the processor that I designed at the NC State, and then a version of it for the commercial product that we made, used 64-bit instructions, and I attempted to do multiple functions each cycle. So you could do an add of 2 numbers, multiply 2 numbers, write a result, increment a loop counter, and based on the results of loop count or something else, jump off to a subroutine. That's in one instruction cycle, just one instruction. We actually had one routine for drawing vectors that was a 1 instruction loop, not 1 instruction inside of a loop, but the entire loop was 1 single instruction. It just repeated over and over again until it jumped to another instruction and repeated over and over again.
So would you call that VLIW, Nick?
Very long instruction word. Very good. Yeah, exactly, John. That's what we tried to do. Our idea was to do things for other people like us, researchers, research labs. So we made everything open. All the source code, everything that we wrote, we gave source code to people. There was an assembler, a display language, post-callable libraries. Customers wrote lots of software, and particularly they started writing them after grad students at UNC and at University of Waterloo both developed C compilers because they were tired of trying to program this crazy processor. And then you could use the C compiler to do a lot more innovative stuff. The hardware was also open. We gave people schematics, interface specs, bare boards. People built crazy things. We built lots of crazy things. Lots of crazy things. I've got a website that'll show you some of this stuff. We'll talk about it later. Mary then took it away.
Nick is clearly the architect of this system, but I got to do some of the interesting bits, and the matrix multiplier was certainly one of those. It is an independently programmed coprocessor sitting right there on the main Ikonas bus.
Yeah, excuse me, Mary, but today they call that a tensor core.
Sure. Why not? Yeah. It's not an element in the pipeline. It's a processor that can run completely independently. Of course, it handshakes and all to keep in sync with the rest of the program that's going on. This was my master's thesis project at NC State, and probably I developed a patch subdivision algorithm for it. I suspect it ran enough to get the pictures from my thesis, but that may be all. But the unit was primarily used for executing transformations, again, independently of the main processor. So for the device to run independently, it had to have its own access to the data memory. So there are two independent external buses on this system. In green, that's the system bus that loads the local memories and control. The magenta is another bus that directly accesses the static RAM data store. And the read and write addresses were managed actually on board this processor. So we could do transformations on a display list of points that are stored in the static RAM, and that could just run independently of whatever was running on the rendering engine, if that's what the rendering engine was doing at that point. Like the 2900 processors, it was microprogrammed, so there are two memories that were loaded from the system bus. A 1K by 16 coefficient memory in red for the coefficients for the transformations, and the local 1K by 32 microprogram memory in blue. It was a 32-bit wide instruction word, which was half as wide as the bit slice processor at that point in that incarnation. There were 12 fields in that word, and we used 31 of the 32 bits. Once the microcode coefficients in memory were loaded, the processor just worked independently. So an idea of how this maps to the actual board, we flip the board around now so it lines up better. The green is the control logic for the main bus. The purple is for the auxiliary bus to the static RAM. The blue is the program memory. The red is the coefficient memory. Now that scruffy looking stuff down in the lower right are some proms. So just remember that there was one more bit of microcode memory. And we never want to let a microcode bit go to waste or a few square inches on a circuit board. So to improve the performance of reciprocal lookup and to support perspective division, we added this reciprocal lookup to get seeds for the Newton-Raphson method. We didn't waste that bit. We didn't waste that space on the board. So what did they look like? This is the first prototype. It's an 8-bit frame buffer. We built it in the back room of our rental house over behind Wendy's on Western Boulevard in Raleigh. The boards were about 12 inches square with 10 inches square of usable space for logic. And we retroactively named this prototype system the RDS, Raster Display System 1000. In 1979, we began delivering the RDS 2000. Couldn't afford a real PDP-11 with a unibus as a host. So we bought and assembled a Heathkit LSI-11. It's an 1123. The processor board came completely assembled from DEC. The LSI-11 had a Q bus, and we needed a unibus interface. So we bought a Qniverter and built it. Took Q to unibus, and then we did the custom interface for the Ikonas. The board size became a severe limitation for us. For in the next generation, we moved up to boards that are about 15 inches square. In late 1980, we began shipping the RDS 3000. And the left center, there's a processor board. You can see the 2900 series chips here, the 8 of them. The two front boards are static RAM boards that I designed. The lower right is the microcode memory, and it has a direct interface to the processor board. You can see them not connected here and then connected. And then the one on the left is the static RAM for the data store. In this picture, those are frame buffer boards, and then the video output board. And one of those would be the frame buffer controller, and one of them will look up tables. You can't really tell from here. With their multiple processing units and wide instruction board, this really enabled our users to do a lot of innovative application algorithms, and Nick's going to talk about them.
So as we said, we made this really for research labs, and that's where the vast majority of our customers were. Universities, let's see, University of Texas at Dallas was the first customer. Turner at Bell Labs was the second customer. Henry at UNC was the third customer, and then it just kept on snowballing from there. A lot of aerospace. My original research project at NC State was sponsored by NASA to look into ways to create cockpit displays. So all the aerospace companies bought systems, a bunch of government and corporate research labs. It wasn't a system that got used a lot, not in like, somebody bought multiple copies of it. The only people that did were some people who made systems for visual scene simulation, graphic art systems, and some medical imaging. So, these were the primary applications, some real-time graphics, some rendering, people doing simulation-based design. A lot of people doing CGI in the early days used our systems. Robert Abel bought a system. Lucasfilm bought a system before they spun out as Pixar. George Joblove and Doug Kay bought a system at Marks and Marks very early. They were probably the first ones out on the West Coast. And Dave Sieg, who ended up with like 7 systems from the omnibus collapse, 7 Ikonas systems there in this basement for a while. Some were used for remote sensing, Landsat imaging and that sort of thing, medical, seismic. And then we shipped some systems to the Maryland Procurement Office, and we're not quite sure what they did or who they were. But
They always paid their bills.
But they always paid, as Mary says. So let me give an example of what you could do with this thing. Tim Van Hook in 1985 came up with a really clever way of creating a linked list of depth elements, dexels, at every pixel on the screen. So you had the front and back surface of a solid at every place, and they were linked together. And that meant you could define solid regions within a buffer, not just the front Z buffer version of it. So it's an extension on that. And you really needed this kind of processor to be able to do this sort of thing. One of the things that he did with it was constructed solid geometry. You could real-time subtract a tool from a solid. So this was a milling machine application, but you could interactively use this tool and nibble away at a solid because you had a complete solid definition within this dexel structure. There's videos on the web. We'll get that.
Hey, Nick, is this a precursor to voxels?
It's like voxels. It's sort of related. Dexels, voxels. Voxels can be much larger or smaller. These were always pixel sized, but deep, if that makes sense. One of the things that Tim did was to write a ray tracer. He used this structure, so instead of just finding the front surface of something and the color of it, for example, he had a pointer back to the UV coordinates on a bicubic patch. And so he could get the normal and any other information that he had about transparency, reflection, and things like that. So this is anti-alias ray tracing. It was done entirely within this graphics processor, which was designed in 1979. It didn't run real time. That would have been really amazing. But it ran about something like 100 times faster than anybody else's computer at the time. What resulted from all this? Well, we sold about 400 systems. Most of them were research lab tools. There's a link there that you may be able to see. Anyway, graphicshistory.org. I've got a bunch of stuff about strange old hardware on there. Tim and Mary and I started a company called Transept in '86 to make a similar sort of board that would plug into Sun workstations. It had lots more functional units, multiple integer processors, floating point processors, lots of stuff 200-bit wide instructions. It can do an amazing amount of stuff within every instruction cycle. And we targeted mostly at doing computing plus graphics and imaging. Although most of the applications really became visualization, because the computing people always wanted to do virtual memory systems, and we threw up our hands at that. The only follow-on after that was the Sun VX MVX, which had a short life. It used multiple i60 processors and included Curtis's GX processor on it to create additional graphics. And if there's any sort of DNA left, it went with Tim Van Hook. He was the graphics architect for the Nintendo 64 graphics chip, GameCube, and was a founder at Artex, which was bought by ATI. That's it for here.
I met Nick, I don't know, back in the 80s, and I, talked to him at various times and places, including his basement where he's got all this stuff. And I've never heard the whole story like this. This is really great. So now we've got the whole thread. While Nick and Mary were breaking barriers, there was this crazy Hungarian professor in North Carolina who had an idea that every pixel should have its own processor. And I remember Henry telling me about that at SIGGRAPH a long time ago. And at the time, I thought, this guy is nuts, right? But what Henry knew that I didn't was that Moore's law worked, and it was going to keep on working. And he had the vision to see out into the future that was going to happen. And so he created a hierarchy of processors down to a tiny processor per pixel eventually, but his team couldn't wait. So they did it the hard way. They built one processor at a time. And Henry, tell us, how many of those processors did you build, Henry?
Thank you for the introduction, John. But the first thing I want to mention is that the head of the lab that Nick and Mary and Turner and others was a crazy Hungarian named John Stadhammer. So I certainly don't want to claim to be the crazy Hungarian graphics professor.
Can't have too many crazy Hungarians.
John was a really wonderful guy. And the other thing I want to say is I just loved our Ikonas systems. From the first day that Fred Brooks and I visited Nick and Mary's house, we walked out, and I remember we weren't sure they were going to really do a company. And we looked at each other and we said, even if they don't do a company, we'll pay them as private people to build a prototype for us. The Ikonas system was so much better than anything else available that we didn't want to go with anything else. And it was so much better for many, many years, even in the mid 80s when our friends started SGI and had a lot of press. We didn't get the first SGI systems because within the lab at UNC, we kept saying, wait, why would we want a system that's slower, that's less flexible, that doesn't do half the things our Ikonas does? So we did lots of great things with Ikonas system, and I'm really sad that John Polton couldn't be here. I think that it should be noted that he was the one who was really the hero behind this. I may have had the germ of an idea, but I gave one lecture about it in the VLSI course that I was teaching in 1980. And I remember he came to my office afterwards and said, this looks a lot more interesting than what I'm doing now for a term project. Can I still switch? I said, you bet. And with that, we started working together for, let's see, from 1980 till the late 90s. And Nick and Mary were eventually part of UNC Computer Science. So there was a 20-year time period during which we built a succession of systems, a few of which, in fact, got commercialized. So as you mentioned, John, even though it started out as there was one tiny processor per pixel, that wasn't the main idea because there wasn't enough power to be able to do real-time rendering. And so I think Steve Molnar found, I think Andre State may have found this old introduction to it on YouTube. And I think Steve was going to play a few minutes of it.
I'm Steve MOLNAR. I was a graduate student at UNC Chapel Hill, and I immediately I looked at different research groups when I came, and immediately decided that I wanted to be part of this Pixel Planes group that had just built this huge machine and taken it to SIGGRAPH. And so I started from there, and then stayed with that group and did my dissertation and worked on Pixel Planes 5 and then Pixel Flow, which had a lot to do with my dissertation. So let me just cue this video. It'll give some of the ideas behind Pixel Planes and more succinctly and faster than I think we could do by hand. And it's old, it's from '87, so it's low res, so just it's retro. So
this is the current prototype of the Pixel Planes graphics system at the Microelectronic Systems Laboratory of UNC Chapel Hill's Department of Computer Science. The system rapidly generates realistic, smooth-shaded images of three-dimensional objects and scenes.
This is Pixel Planes 4.
The machine's simplest software executes a Z-buffer visible surface algorithm from a scene description stored in a conventional display list. The only unusual aspect here is that the description of each polygon is broadcast into the frame buffer, and all the pixel-level processing is done by the custom so-called smart frame buffer. That is, there is no rendering engine outside the frame buffer that converts a polygon into pixels and then stores each pixel in a conventional frame buffer memory. The display list, its traversal, the geometric transformations, and the conversion to Pixel Planes commands are all handled by a pipeline of 3 commercially available array processors made by Mercury Systems. They are shown here on the top rack. The Pixel Planes commands are sent to 2048 custom memory chips residing on 32 frame buffer memory boards. Each board contains 64 custom chips. Each chip contains memory and processing for 128 pixels. The heart of the system is this cluster of custom frame buffer memory chips, which perform calculations in parallel at every pixel with very little dedicated circuitry. Each chip contains, in addition to the usual pixel memories, a 1-bit arithmetic logic unit for each pixel and a binary tree of 1-bit adders that can rapidly evaluate linear expressions in the screen's X and Y coordinates for every pixel in the chip simultaneously. Fortunately, many pixel calculations turn out to be of this form, that is, linear in the screen space. Calculations of this form are very efficient in the system, since for them, only the linear coefficients A, B, and C, and their operation codes, need to be broadcast to memory chips. Each of these chips has a multiplier tree to calculate the expression AX plus BY plus C, and so only simple bit operations need to be done at the individual pixel level. A convex polygon can be rendered by broadcasting to the frame buffer the linear coefficients for each edge, and having it turn off all pixels that are outside of that edge. All the pixels are on at the start of the polygon, and with each edge, more and more pixels get turned off, until at the end, only those pixels inside the polygon are still on. Hidden surface calculations using the classic Z-buffer algorithm are also done simultaneously for all pixels in a polygon, using a single A, B, C linear coefficient set. These are the coefficients of the plane on which this polygon lies. Each pixel compares its new value that it receives from the multiplier tree with the old Z value that it's storing in the Z buffer. Shadows can also be calculated efficiently with linear expressions. Note that the shadows of one object can drape naturally onto and around other objects. They are not simple polygons painted only on the ground. The shadows are now being turned on and off for emphasis. A scene with shadows is calculated in about twice the time of the same scene without shadows. Here we show an extreme close-up of the screen to demonstrate our first anti-aliasing method. The staircasing artifacts are minimized by successive refinement over sampling whenever the system has spare time. That occurs whenever the user stops moving the object. At these times, the system continues to calculate additional samples within each pixel and filtering appropriately. Whenever the user is moving the object, however, the system abandons anti-aliasing in the interest of speed. Circles are displayed essentially as polygons with one edge because the nonlinear terms x squared plus y squared are constant and are pre-stored in each pixel.
So you get the idea. That last idea, by the way, of doing molecules with a single expression is due to Fred Brooks, who started the department and whose principal research area was in molecular modeling at the time.
And Henry, I have a question.
Yes.
Where the hell did you get all those chips?
Wow, that's a story in itself. Thanks to, the answer is that NSF and DARPA supported us. And at that time, there was a major program within DARPA and NSF to promote custom integrated circuit designs in research labs and universities. And it was supported by a separate contract called MOSIS, M-O-S-I-S, for metal oxide semiconductor implementation system. And if one had a contract or a grant with NSF or DARPA, one could send chip designs to MOSIS and they would get it fabricated in a commercial fab and then send back the finished chips. It took a lot of extra work to get the 2,000 chips, and that took some amount of persuasion to get the money for that.
It was half of the MOSIS resource for the entire country for the year of 1986, I understand.
We needed 2,000 working chips, and we didn't think that we could get that many that were perfect. And so we spent a lot of time on how the system could handle chips that would have one or two errors somewhere in the memory or the processor or the tree. And if you look carefully at the boards, you'll notice that there's a whole row which is not populated. That's because we thought that we would need that many more chips, you know, with one fault here or there in order to have a 512 square system. Fab lines are not wanting to tell you exactly what their yield is going to be. One, because they don't know. And second, whether they get a 25% yield or a 40% yield makes a big difference in whether they make money or lose money. And so we expected a 25% yield, and I think we got 41 or 42% yield. So we had more than 2,000 perfectly working chips. Boy, the story that I want to tell, do I have 2 minutes?
Yes, of course.
Why did we build a system with 2,000 chips?
That's the story.
All the time that we started from 1980, 81, 82, 83, John Polton, who was really leading the team, you know, I cheer on and I come, but John Polton would say, you know, we're never going to build anything with more than hundreds of chips because it's just not reasonable. So we presented the algorithms for pixel planes 4 at a SIGGRAPH in 1985. So we said, how fast would a full-scale system run, full-scale 512 square? And the student, one of the student authors, Jeff Holtquist, I think, some of you may remember, presented the paper. And of course, you remember SIGGRAPH is this gigantic venue. And then he would show these simulated results, you know, like the polygon that you were seeing with shadows, the molecules. He was only showing like a small molecule, you know, a simulator, like a little drug. And then he would say, we think that we could run this at about 13 milliseconds, you know, 13 thousandths of a second, you know, fully contoured with interpenetration of the molecules. And I remember distinctly when he said 13 milliseconds, there was guffaw around the hall. And after the session, we were standing in the outside in the hallway. I said, was there really guffaw? Did they really not believe us? And all the other people said, yep. I don't think they believed us. And one of the other co-authors, Jack Goldfeather, said, now, why is it that we're not building a full-scale system? And I said, because John Poulton says we shouldn't build anything if it has 1,000 chips or more. He said, why not? We all look at John. Well, maybe we could build it with 2,000 chips. And therein we decided we would try to build a full-scale system. And the next year we came back with a full-scale system. That was the one that you saw here in the 1987 video. So if it weren't
13 milliseconds.
Oh, yeah. That was easy. I mean, that was just a little drug. But, you know, the big protein was many, many times that long, but it still was running at whatever it was, 30 milliseconds.
Yeah, that's.
But
I mean, one of the great things about it being incredibly SIMD is it, you know, once you've got one of those things at every pixel, it doesn't, you know, more pixels, it's the same amount of time.
Right. So the next big thing was really the realization that as you get more speed and you get more complex, then you could put more polygons in, the average size of those polygons or those spheres gets smaller, which means that you're using less of your resources all the time. Is that clear? So the big jump, right? Because, you know, now you say, here's this polygon. If all you have are 40 atoms, that's fine, okay? But if you could do 400 atoms, then each of them tends to be smaller, right? And that means if you're using your whole screen worth of processors and linear expression evaluators, then you're not using a large fraction of your resources most of the time. And so the big challenge for us, Steve MOLNAR, Mark, when did you join? Pixel Planes 5, right?
I was, Pixel Planes 5 was already built when I joined, so I did get to use it and code it. And then I was there for the development and implementation of PixelFlow.
Who was that guy that was just talking?
Oh, hi, yes. I'm Mark Olano. I was a grad student at UNC during from 1990 to 98, which is maybe a cautionary tale not to tie your success or failure of your dissertation to a piece of hardware working and being done. And my dissertation was about basically taking shading languages like RenderMan was sort of the inspiration and getting it to run on these crazy beasts.
In fact, Steve, you might be the right person to say, what was the jump from Pixel Planes 4 to Pixel Planes 5?
Well, so as Henry said, with this rendering algorithm, the first thing that you do is you figure out what pixels are within a given triangle. And when they're small, you just exclude everything. And now you're just working on a small number of pixels. So what we decided to do to improve the utilization was to tile the screen. So the next generation, Pixel Planes 5, you could decide the number, but a number of tiled rasterizers. Each of the rasterizers was 128 by 128 pixels. And it was responsible, it could move around and render any number of 128 by 128 pixel regions of the screen, and it received the rendering commands and coefficients for pixels for primitives in a given tile. Then it would process all of those, figure out the final frame buffer values for those pixels, send them to a frame buffer, then move on and do the next one. So this next system that we built was a more complicated machine. It had to have more geometry processing. So we did a couple of versions of that. Well, I guess we had a parallel geometry processor, and there was some complicated software that took the transform primitives, bind them together, and we had a hardware network for transferring those transformed primitives and their instructions to the different rasterizers. and then the rasterizers just moved around, tiled the screen, went to the frame buffer. So one of the things that we also realized, though, was we started investigating more sophisticated rendering algorithms like Phong shading and more complicated shading and lighting. And we started procedural textures. And one of the things we realized was there was a lot of processing involved for those. But if you did all of your rendering for all the pixels, and then you stored the intermediate values for this whole tile, then you could run our SIMD processors in parallel and do complex shading like Phong shading for all of them in parallel. And you had this immensely powerful machine that could make quick work of these calculations if it was doing this whole 128 by 128 array in parallel.
And for anyone who's thinking about, oh, good, I get to write my, GLSL or HLSL shading code. Each processor on that one had 208 bits of memory. Fortunately, it was with a 1-bit ALU, which meant that you could decide exactly how many bits long something could be. It didn't have to be a multiple of 8. And we definitely didn't use multiples of 8 for a lot of things. So it's like, oh, that could be 7 bits because that'll save me a bit that I can use for something else. Could do floating point, although floating point built out of 1-bit operations. And I think as I recall, the code was mostly macros that ran in the C code that then generated the instructions for these things. So it looked kind of like you had assembly code for your shading code kind of embedded in your C code that was describing the geometry.
So Mark, what year was that?
Early 80s. I don't remember the exact year. Do either of you?
Pixel Planes 5 was in the 1989
early
to 1990.
90s.
90, 91 range.
So,
early 90s, not 80s.
So just to put a pin in the calendar, what these guys did is they did deferred rendering, which is now a big deal for tiled systems that you use in your smartphone every day.
Mhm.
And what they did was tile-based rendering, right? Well, then Microsoft reinvented that in 1991. They called it Talisman, right? But these guys did it first.
So we should turn the crank one more time to PixelFlow, which was the next generation. And there were a number of things that PixelFlow had there were several ideas behind it. I think the one that most people associate with it is this notion of a depth compositing architecture, where you have a portion of your primitives on one graphics processor. It renders the complete scene, including the depth buffer, and you have many of these in parallel. And there was a hardware compositing network that would just combine them together at video rates. And so it made a linearly scalable system. So it did that, and the triangle rates, the polygon rates went above 20 million per second on that system. It was a big system that we built, but there were several other ideas behind PixelFlow. One is we increased the width of the processor from single bit to 8-bit because we were doing more computation, and we had in mind, as Mark said, doing real-time programmable shading. We built a floating point library so you could code your shading algorithms in standard floating point. It wasn't always 32-bit, but it was floating point. And we also built a texture subsystem. So there was texture memory, and there was hardware for taking UV values, doing the divide by W, calculating. That was done on the enhanced memory processors, but streaming those values out, doing texture lookups, and then filtering the values back and generating textured images. So
I remember at one point telling Turner Whitted how much texture memory there was per render board, and he told me, no, you've got to be mistaken. That has to be for the entire system.
And
We should
today,
probably mention Hewlett Packard's generous collaboration with this and licensing of this and setting up an entire laboratory near UNC for this and pouring in a large number of millions of dollars into this.
and the incorporation of division.
Yes, Division first licensed it, and then there was Hewlett Packard.
Mhm.
But it was a big effort and lots of, I would guess, in terms of people power, probably at the end, more HP people. Steve, Mark, you would probably understand more, but I think there was a substantial number of HP people.
Yeah, I think there were, I don't know, close to 100 people working on
Yeah.
this at the peak. And Mark, you should show that the screenshot of the real-time programmable shading that we're able to do on PixelFlow.
Yeah, so let's see. Well, maybe not that. That's
That
what I was
one, oh yeah.
at the beginning of this. How about this one? So this was an image that was inspired by the cover of the RenderMan Companion, which was a book about Pixar's RenderMan that they used in their movies. But we did it in real time on PixelFlow. We were talking before this started about whether these images were from the simulator or from the real thing. And I'm not 100% certain, but I think these were probably from the simulator. I found them in the images folder of a paper that probably would have been simulated work. Unfortunately, and maybe someone else on the call can help me out with this later, I have a lot of Word documents and PowerPoint files that Word and PowerPoint will not open anymore because they're too old. I think I also have some U-matic tapes that may have had actual video of this that I have no way of playing anymore. So we should figure out a way to resurrect those.
Yeah, Mark, you can open those things with LibreOffice.
Oh, okay. Good to know. In PixelFlow, this is a shading language that does look a lot more like modern shading languages. It was very much more modeled after RenderMan. So the shaders that you wrote were surface and light rather than vertex and fragments. The one in the bottom left was part of a demo where you could sort of click in various spots and it would make ripples in the reflection map real time, which is more fun live than it is in an image. All of those others were ones that I or some of the other people working on the system wrote. These two were shaders written by people on other projects at UNC, not connected to the PixelFlow effort, which I thought was a real watershed moment to have shaders written by someone who was not involved in making the system happen.
These are big system projects, and we're a university group, and we're a big university group, but still it was difficult to build a system like that, and it needed lots of work in different parts. So we had to convince people to join the team and to help out with the project. But to do that, it had to make sense for their research. So we, as part of building these systems, we had research projects in bidirectional simultaneous signaling, in thermal design. Somebody got a patent on the heatsink design for PixelFlow, and the clocking scheme. We couldn't just use standard clocking because everybody does that. So the clocking for PixelFlow used standing wave-based clocking, which is a novel way of distributing clocks where you have no clock delay because there's no information passed around. So it was a system built with all kinds of risky research projects, making the underpinnings of it. And it's kind of miraculous that it all came together.
Yeah, it definitely was a big help that we had the companies involved like HP and Division. As a grad student working on it, I mean, some of the work you're doing is cutting edge research, but there's also a lot of I need to write a matrix multiply because we need a matrix multiply, and I'm not going to get a paper out of the fact that I wrote a matrix multiply for a new crazy system. So I couldn't use another existing matrix multiply library because new crazy system. But somebody's got to do it. So there was definitely a lot of non-researchy work that yes, the grad students were doing, but I think it was definitely for a project like this, it was really important that we had the corporate help too, because that meant that we weren't all trying to put a crazy research spin on absolutely everything.
Well, these guys were building these crazy machines in North Carolina. They weren't the only ones who had the idea to build such crazy machines. And there there was a little group that Pete was associated with. AT&T thought that they could build a super pixel processor. I don't know what possessed them to think that, but that was their big idea. And Pete helped that. And so I asked him to bring some pictures and show it of it. I just have to make a side comment that Pete has one of these things in his house. It's a coffee table. So Pete, tell us the story.
So basically, I had the fortunate happenstance of running into Mike Potmusel coming out of the cafeteria at Bell Labs one day, and he said, "Hey, we're doing some really cool stuff in this new group that we're calling Pixel Machines. You should come down and take a look." And what it was an entrepreneurial spinoff at the time where Bell Labs was actually willing to invest in companies within a company, and we debuted the Pixel Machine at SIGGRAPH in Anaheim in 1987. We carried on with this really big box for a while. In 1991, we tried to turn it into a PC card graphics accelerator. At the time, AT&T decided there just wasn't enough profit in it. So basically, they disbanded the organization, at which point I then licensed all the software, started my own company called Spotlight Graphics, ended up licensing the software to Bentley Systems, and the ray tracing and photorealistic rendering software was actually in production as part of MicroStation through about 2009. So a nice 22-year lifespan on the software, which is pretty cool. Yeah. The original Pixel Mechanics, Michael Potmusel was the software guy and kind of came up with the original idea, and Leonard McMillan was the lead hardware designer. And then we had a bunch of really cool software people and a bunch of really cool hardware people. The reason I have an asterisk on Leonard is because not only was he the chief hardware architect of the Pixel Machine, he also actually wrote the original ray tracing core, which I then took over as soon as he got bored and wanted to start building some more hardware. The architecture was actually pretty cool. We actually had a pipe node pipeline where we would chain anywhere from 9 to 18 pipe nodes that could do transformations and things like that, feed the data then into an array of anywhere between 16 and 64 pixel nodes. Supposedly, you could buy a machine that only had 16 pixel nodes, but realistically, anybody that wanted to do anything just got the 964 with the 64 nodes, because if you're going to do it, if you're going to spend money, you might as well spend it and get what you really wanted out of it. And the big one was sold for about 150,000. So a nice inexpensive product. One of the taglines in our videos was, for the cost of a typical workstation, which okay, everything was expensive back then. We had a 1280 by 1024 32-bit RGBA buffer that you could do at 60 hertz. There was enough video RAM associated with each processor that you could do single, double, and even quad buffering, which was pretty cool at the time. The heart of it was we were using this Western Electric DSP32 signal processor, which was a really cool chip in a lot of different ways. First of all, you could essentially get 10 megaflops per chip, and we had 82 of them in our box. We had 820 megaflops, which at the time was just completely absurd. Now, of course, you get that in an Apple Watch. But the coolest thing was that it actually had 32-bit floating point with 4 40-bit floating point accumulators. It had combination multiply accumulate instructions and a whole bunch of registers on chip memory, and even an interface to be able to talk between chip and chip, which is pretty cool. It was a fairly C-like interface. The assembler was actually fairly C-like, which is pretty cool. Here, basically, what we're just showing is a floating point register. You could do the multiply and add in the same instruction, and the data would be available 3 instructions later. But the cool thing about that was, if you actually were working on things like RGBA or XYZW, essentially you could do them all sequentially, and by the time you were finished with the 4th one, you were able to get the data out of the first one. Originally, there was a C compiler for it. What we would typically do is we would write the program in C, compile it once, and then from there on, we would just tweak the assembler. Between trying to populate all the delays and it just, the C compiler just wasn't quite good enough. So we basically wrote it almost all in the assembler after we had the original code.
So you guys were the compiler.
Well, I mean, they did the first version, but then after that, we just did it all and tweaked. So this is one of the pipe boards, and so you can see that it has a 3x3 array of the of these DSP32 chips. Each chip had 9K words of program space. That 9K SRAM was actually used for program and data. So you didn't really want to do a whole lot of work in any one of these nodes. But the cool thing was, what you could do is you would basically pipeline them sort of Unix style. So we would have one node that might do super quadrics and splines. The next node might be transformations. The next node would be culling, projection, clip. We'd actually have one node that would clip X, one that would clip Y, one that would clip Z. Just so we could make it flow through the pipeline pretty quick.
So Pete, I don't know if you know this, but I actually worked with a pixel machine at the University of Illinois when I was an undergrad before I went to go work on pixel planes and pixel flowish things. And one of my favorite things about that machine and the pipe node board was they had a little red, green, and blue stoplight LED set per node that would tell you if its input FIFO was getting backed up.
Exactly.
Which I really, and you could kind of watch that like backing up to the previous nodes and everything. I thought that was very clever.
Yeah, that was definitely cool. We had a lot of fun with that as well.
Yeah, Danny Hillis copied that with thinking machines.
The one last cool thing about the pipe board was that the very last pipe node would then broadcast its data to all the FIFOs of all the pixel nodes at one time. So essentially, we were just broadcasting the data, which was very, very, very efficient. So this is one of the pixel boards. Again, you have 4 pixel nodes across the top there. The same 9K program and data words. The big difference here is that there was a whole lot of VRAM and a whole lot of DRAM. When we were doing our GL style rendering, we would use the DRAM for a 32-bit floating point Z buffer, which again was kind of revolutionary at the time. There were integer Z buffers, and I think there might have been one 16-bit floating point buffer, but to be able to do 32-bit floating point was pretty unique. The other thing that was kind of cool is you actually had a serial connection from each DSP to its nearest neighbors, so you could theoretically pass data back and forth between them. And we had little jumpers. You can see on the very bottom of the board, there were actually jumpers, so you could connect the boards together, so they could actually talk to each other. We didn't do it very much for rendering. It was mostly used for image processing, edge detection, for analysis, and stuff like that.
Pete, did you ever consider using that communications to build a hypercube?
It was sort of, we sort of had it in our spec that you could have a mesh computing system, but we didn't. Nobody really got there. I mean, we internally kind of focused more on the rendering side. There were a couple of customers that did look at doing some things like that, but I don't really think they had very much success, to tell you the truth.
So you could have then claimed that you preceded the transputer.
We could claim a lot of things, I suppose. Software-wise, we had a lot of software that ran on it. We had what started out as PicLib, which was our picture library, eventually turned into ArtLib, which was our advanced rendering library. It could do, GL style, ZBuffer, anti-aliasing, compositing. We had these things called atoms, which are Phong shaded spheres. We did RGBA Z templates, which were essentially pre-rendered geometry that you could sit there and then you could stamp them around a scene. So a lot of times people would use that in like simulation. Like if you were doing military simulation or a flight simulator, they'd have these stamps of trees that you could pop around. We had the very first commercial ray tracing library where, up until that point, anybody that wrote a ray tracer basically wrote their own ray tracer. So what we did is our ray tracing library was basically GL style. You basically would define all the geometry, define all the lights, and then you would just say, you would invoke ray trace, and we would automatically build a bounding volume hierarchy, and then we would start doing the ray tracing. The Z buffer renderers would use for the Z buffer. We actually use that for ray tracing database storage. So we were able to take advantage of that, and we could then use that 512 megabytes for the data. We also had a bunch of image processing libraries. We did have a little foray into simulation systems for vehicle, aircraft, maritime. People experimented with it. I don't know if they actually made any money off it, but at least it was kind of a fun project. And then we had this devlib library where people could do essentially any programming they wanted for the Pixel machine. And one of the cool things that I got to work on was we actually did some Mandelbrot and Julia sets in real time, which was kind of neat. Benoit Mandelbrot actually came to our lab one time, and I got to demonstrate the Mandelbrot set to him, and he was very impressed. And that was actually kind of one of the highlights of my career at the time. So we have actually a couple of rare live screen captures that I actually found on some old videotapes. So this is a scene that was done. Eric Haynes, who was at 3DI at the time, he had what he called the standard procedural database. And this was 7,381 chrome reflective spheres with 3 light sources. And when Eric was rendering it on his workstations, it was taking between 4 and 5 hours, and we were doing it in 16 seconds. So we had like 3 orders of magnitude improvement, which was pretty cool. Turner-Whitted, of course, we all know this image. When Turner did this, I had a measurement of his from 1981 where it took him 78 minutes, and then on a Pixel machine, we could do it in 15 seconds. So a nice little improvement. The next part here was actually kind of cool. I think we were the first ones that actually had an interactive ray tracer. We actually got to demo this in Atlanta SIGGRAPH in 1988. What I would do is I would actually take the chrome sphere and I would attach it to a mouse, and I could actually drag it around. By 1988, we were doing this, I think, at about 6 frames a second. And so it was actually cool to do interactive ray tracing. I'm just going to show you the pretty cheesy demo reel. I left the cheesy bits in just because they're kind of fun, but this is some of the things that
no longer does it take a huge investment of time or money to achieve high-quality graphics and image processing. Today, for less than the cost of a typical workstation, you can extend your graphics power several orders of magnitude with the supercomputing capabilities of the Pixel machine.
This was John Mitchell.
3D rendering and animation. Real-time simulation.
That's what they call it, real time.
Image processing. Scientific visualization. 3D rendering and animation. The Pixel machine offers a rendering and animation solution to fit almost any budget or artistic objective, from flying logos to highly detailed, captivating models. With the Pixel machine's 3D rendering and animation libraries, ArtLib, RayLib, and PicLib, you can create high-quality graphics for interactive modeling, data visualization, and realistic rendering. Complex visuals like this, using ray tracing, would take days to render on a conventional supercomputer. But Electric Image did it in minutes, using their Synthicam software and an AT&T Pixel machine, the world's fastest ray tracing engine. Powerful animation software makes the Pixel machine easy to use. Circuit Studios, producers of this sequence, use the Pixel machine to render scenes ranging from fantasy to public affairs programming. Powerful, programmable, affordable. Put the Pixel machine in creative hands, and there's no end to the graphic heights you can scale. as the British production company Infinity demonstrates here.
The funniest thing about the Infinity video is I remember when I first got the video from those guys, first thing I did was I called them up and I said, so Mike, there's Mike Wickens at the time. I said, what did you use to create all those images? And he said, we just used your ray tracing library. I'm like, no, really, my library can't do that. Really, what did you use? And it was literally just the ray tracing library. And I was completely blown away. And it was kind of one of the first times where I really understood that, you can write the best computer programs, but when you pair it up with great artists, it's amazing that you could do so much more than we could just do as programmers. And I really learned a lot back then.
So Pete, did you do that water hand at the same time the Abyss was made, or did you do it before that?
That was
the Abyss was done in '89.
Yeah, this was right around the same time. So I'm guessing it was probably done afterwards, but I can't swear to that one.
We call that an homage.
One of the interesting technical challenges I had, which was kind of fun, is as I mentioned, we had this 512 KB per node that we could store databases, but that was really limiting for what you could actually ray trace. So I actually had to develop a technique where I would split these things into pages, and we couldn't use addresses at that point. Everything had to be a page number, a page index, and an offset. And then what I would do is after we sent all the data down to the pixel nodes, we didn't really need the pipe nodes anymore. So what I ended up doing was turning the pipe nodes into a cascading page cache, where the most recently used pages would be at the bottom. And as things got stale, they would kind of keep getting pushed up or pushed out to the host. And it was really kind of fun to do that sort of thing. And it was a nice creative challenge. One of the things that we kind of learned there was that, it definitely made a lot of sense to, you group all your bounding volumes into one page, all your geometry into another set of pages, and materials into another, so you could easily page them in and out, which it was a fun challenge as people started to push the technology, to push the limits of what we could actually do. It was pretty cool. So one of the things also going through some of these videos, I did come across a few blasts from the past, so I'll just show you real quick. So here's one of Dan Sandine in one of the few times I think anyone's ever seen him wearing a suit, which was interesting on its own. He was I think he was at USC at the time, working with the Pixel machine. And since Donna Cox just retired, I thought I'd actually pull this one up. So this was Donna in 1989 on one of our AT&T video magazines. So as I mentioned, there were alternate uses for Pixel machines. One of the things it turned out is it made a really good pizza oven. These are the lights that Mark was actually mentioning. The 16 rows of lights on the left-hand side of this image are the pixel nodes. You can't really see the pipe nodes too well. But the one thing that we learned was that if you were ray tracing with 820 megaflops of processors in there, it got really, really hot. And we accidentally discovered that if you left a pizza sitting on top of the pixel machine, it would warm up very, very nicely. And as John mentioned, it does make a very nice $150,000 end table, which has been sitting in my basement for a very long time. I did have to take all the boards out of it because with all the boards in there, it definitely weighs, I think, over 220 pounds. So took out the boards, took out the power supply, and I just use it as an empty shell. And that's the Pixel machine.
If I remember right, I think it came with a BTU rating.
It did. It was amazing that we could heat up a room very, very quickly.
Going from these giant machines and taking advantage of Moore's law. Curtis Pren was at Sun at the time, and he had a different problem. He had to try and take what you guys were building that filled boxes and racks and cram it into one little board, and then cram that into a Sun microsystem. And he actually succeeded in it. And in fact, he was so pleased with what he did, he started a company afterwards. And I'll let him tell you that story.
Okay, thank you, John. There's actually a series of graphics cards that we did, and one led to another that led to another. And I won't go back to the graphics I did in high school or in college, but the first job I got was up in Upper State, Vermont at Burlington. And we mainly did multi-bus boards, like 8-bit index boards. And we actually won the contract for a board. I'm going to do this old school because I'm on an iPad, but this is the IBM PGA board, which is the first accelerated graphics card in the PC industry. And it's a 3-board, 2-slot system. The tiny board in between is a CGA emulator, and it actually has an 8088 as a processor on it. And what you see on the front is all the memory that's related to the color graphics. The other card that was in the PC at the time was actually the MDA, which is the monochrome display adapter. And so this one had a full interface that you could program to render 2D. You could actually render 3D. It was broken in a little sense because we were dividing by Z, but it really didn't matter because it didn't have a Z buffer involved. But what was important about that project?
With a 6 megahertz 16-bit bus.
Yeah. And what was important about that project was to realize that it had an 8088 on it. And so it came out at the same time that the AT came out, which is a 286, and a much higher form factor. So we could have done it in 2 cards or 1.5 cards, and we were really upset about that. But so we had the 286 and 287 in the lab and running this on it. And it turned out to be on an XT, which had an 8088 in it. It was actually a pretty balanced system. Half the graphics was being done on one processor, and the CPU would take care of the application. When you put it on an AT with the 286 on it, it turned out it was actually okay, but nothing to write home about. And then when the 386 came out, there was an interesting phenomenon that happened, which is if you ran your application on the 386 and on the PGA, it ran, but if you removed the PGA, it ran faster. And that was the first lesson that we learned about graphics, trying to do it for the masses. And it's always intimidating to be around all these diehard researchers and what they've come up with, and basically unlimited power and size and weight. But we were always trying to do stuff that would be sort of for the masses, and that kept us to a certain form factor. But on that project, I was the architect. John Montrim wrote all the code. He was fresh out of MIT, and he went on to be one of the architects at Silicon Graphics. And then I got him to join Nvidia, and he became our chief architect. While I had in the evening, while I had the AT in the lab, I actually wrote a ray trace program. So I claim it's the first ray trace image done on a PC. And that was because there was a 287 involved. And it was an IBM flying logo that had self-casting shadows and anti-aliasing. And right now it's over. The only printout of it is actually in the IBM museum. The other thing I did was I loved or wanted to do flight simulators. And so I actually worked on an A10 Warthog flight simulator on the Atari 800. And I was no John Carmack, who could actually run wonders around a VGA and just software only. But that sort of got me thinking about how you start doing computer gaming and graphics. So I moved out to California, worked for Genrad for 2 years, and I got really upset about working on an Apollo workstation and trying to do schematic capture. And so Wayne Rosing, who actually did the Lisa at Apple, he had a bunch of PGAs, and he was in charge. He actually was in charge of hardware development and also became the leader of Sun Labs. And so he hired me and asked me if I could put the PGA on every single workstation that Sun sold. And he was being told not to do any graphics because a new graphics division was being formed to actually take on silicon graphics. And so the one thing we were really scared of is that the CPU could actually catch up with us. And this was in the time of like the 68,000 and just starting to talk about the first RISC processor. So what we created was, well, what we knew we had to do was actually do everything in silicon. We couldn't use discrete components like the PGA had. And we limited ourselves by saying, if we ran at the speed of the memory or the frame buffer, then there's no way the CPU could ever catch up with it. They could match our performance, but they could never exceed our performance. And it was interesting also that the CPUs were going down one path, which was they were starting to stick on large caches. And then they created a second level cache and a third level cache. So they were actually moving further and further away from the memory. So what we did was we sort of looked at what was needed in the workstation. Because we were a closet project, nobody was reviewing what we were doing or how we were doing it. And the first thing I did was hire Chris Malachowski, who actually was a co-founder at Nvidia. And he had done CPUs at Hewlett-Packard and didn't know anything about graphics, but he was bored with CPUs. So I'm saying, okay, I'll teach you everything you need to know about graphics. But that was a big lie because I lied to him on every single step through the process. But he very quickly got that the bandwidth was everything. And he started working out how to design these chips in basically combinational logic. And there was one story where the 3D graphics group came running over to ask him how he was doing edgeless, because on our frame buffer controller, he actually was drawing 2 lines at once and filling in between them. And he says, it's just combinational logic. And we're like, where's your edge list of the points that you need to draw between it? It's like, it's just combinational logic. And so we just had a totally different attitude to how to do it. So the original, I got a picture of the original team. So hopefully you can see Chris in the background. He's got Ryan on his shoulders. This was up in Lake Tahoe. And so we created 2 chips. And the first chip was the frame buffer controller. And so my old manager, Al Jocko, actually loaned me his boards. And so the big chip down here is the frame buffer controller, and it has 170,000 transistors in it. And it was made out of 1,500 nanometer technology, or 1.5 micron. And so it just did basic workstation graphics. And by basic, I mean, it did Blitz, which is block image transfers for scrolling your images or your text on the screen. It did fonts, which was 1:8 conversion. It was an 8-bit index system, and it did fills. And so because we had to do rectangles and trapezoids and 2D lines, we basically, Chris designed a dual line engine. And so then it basically became filling between the 2 lines. So we could do trapezoids, triangles, and we could even do quadrilaterals or 4-sided random objects, but we couldn't do all of them. So we could do hourglasses, but we could not do bow ties because there was 4 active edges in that. We did also raster operations on it, and we had a 16 by 16 pattern on board. And all of this was working simultaneously. The chip I worked on is the smaller one, which is called the TEC. And that had 212 1,000 transistors in it, and it was also in 1.5 micron. So what it stood for was a transformation engine and cursor. So it had the logic in it to actually control the monitor, timing, and it also had a 32 by 32 by 2-bit cursor. So we could have a 3-color cursor on the board. I wanted to do electrical CAD very quickly, which is just a 2D transformation. And so it had a signed 32 by 32 multiplier in it and a 32-bit adder. And it could do about 50 million transforms per second. And it was mainly meant for 2D CAD because we were only doing flat shaded triangles and lines and rectangles. And so it had a 3x2 matrix inside, and that sort of quickly grew to a 4x4 matrix. And then that grew to a register file of 64 registers. So we could actually have 4x4 matrices in there, and it could actually do transformation or concatenations of the matrices. And then in the corner, I threw in a Newton Raphson divide circuit. So what this thing could actually, and it also could load directly into the FBC, the results. And it took 3 formats: integer, 16.16, and single float, IEEE floating point. So with that, then so I've got 2 more diagrams. One is sort of the layout of this is the FBC to give you a feeling of all the different components, if you can see that.
Mhm.
And this one is of the TEC, which was standard cell. That the frame buffer controller was actually gate array. And because we had the multiplier, which is here, and then you had the cursor that you can see down at the bottom of the 2 arrays. And then you had the register array at the top, and next to it was the divide circuit. And then the rest of it was control and also the timing circuit. So with that, in my spare time, because I had fooled around with the A10 simulator, I decided to write another simulator, which was called Aviator. And so I'm just grabbing all the little display out. So Aviator, some of you may remember, was the first outside of Silicon Graphics. It was the first networking dogfighting program on a workstation. And because everybody was getting one of these GXs on the workstation, it basically became, and also because Sun was known for its networking capability, it became a very, very popular selling point where the sales force, we had to give the sales force free copies of it, but the sales force would then buy it and actually give it to their customers after they bought a multi-$1,000 workstation. And so what this looked like, as far as images go, is there's an F-18 fighter, and you can see the texture in the background. And if you're from the Bay Area, that is Mount Diablo that you see. And so we had both Hawaii and the Bay Area that we were flying around. And so also with it, it's like, well, you need a game port. And so we actually came up with Hot Ass, which is basically, it's a serial port to plug into your Sun workstations. And then on the other side is basically the standard polling game port for any PC device that you wanted to buy. So this became sort of like the motivation for actually throwing in that divide circuit. But with it also came some unexpected things that sort of was like the leading sort of up to what a GPU is. Because with the array that was in the TEC being 64 registers, and you had this Mac unit, you could actually do like vector matrix concatenation dot product sliding models, and even some people actually did convolutions on images. But the performance, because we worked from the frame buffer backwards, and basically every cycle you got, hopefully all the pixels, being pushed at the same time. We were getting 2D vector wise, we were getting on the base system a 470,000 2D vectors per second, where the Silicon Graphics personal iris, this is the 4D 20, was only getting about 80. And on 3D vectors, we were getting about 244,000, and Silicon Graphics was getting about 80. And then 3D flat shaded triangles, we were getting about 244,000, and Silicon Graphics was getting about 16. But this wasn't really impressive because it wasn't doing grow shaded or Phong shaded or full-blown lighting. It was probably something more about having your window system doing incredibly fast, because the first time that you could actually scroll faster than the frame rate of your monitor. So we actually had to sync it to the monitor, otherwise you'd get tearing through it. And so there was a lot of politics inside of Sun, where we weren't allowed to say, actually at one point we taped out 2 chips, one without 3D and one with 3D, because it was taking so long for us to have a design review. We took both tapes into the to our VP of graphics and said, you know, we're supposed to do 2D, but we have both, you know, pick which one. He went through the roof. There was a lot of fence mending to be done, but he basically picked, okay, go to 3D. And we were basically making all the money for Sun and graphics, but we were sort of ostracized from the 3D graphics group. That was actually they had more engineers, 3D engineers, than Silicon had 3D engineers, but they still couldn't make a go at it. So I've been having this 6-month-long argument with John, which is, what is the first GPU? And finally I had to basically decide what is his definition of the GPU, because he's going to write the book on it. And obviously the GX was not the contender. It did 3D, it did graphics, but it wasn't a single chip. But in our first cost reduction, it became a single chip. So is this the, you know, the original, you know, GPU, because I had floating point?
What year
on
was
it?
that, Curtis?
So this one was developed 86 through 88.
Mhm.
I would guess this was probably 8990-ish. And the code name for this was called Lego.
Yeah, I
Yeah.
remember Lego. Yeah.
Or low-end graphics option. So it's not like low performance, it's just low cost. And so if you have kids, you know that Lego is a toy. This was a cost reduction. We also, so this had a 1 megabyte, both of these had 1 megabyte of frame buffer running at 1152 by 800. And then we had a Duplo, which was 2 megabytes, which could go up to 1600 resolution by 1280. And then we had Quadro, which was a 4 megabyte version. And this is single chip. And so this was awesome, running Aviator at 1600 double buffered, so no tearing. So this is where we actually moved to, and it was a success. And it was actually on all of the Sun products, because we basically designed it to be on every, if you came up with a new bus inside of Sun, like an S bus, we would, add that to our chip and retape it out. So then basically there was friction happening. Well, there was always friction inside of Sun, but as Mary and Nick pointed out, they joined forces with Tim Van Hook, and I blame Tim Van Hook for basically my exit from Sun, because he actually got Andy Bechtolsheim's ear, and he convinced Andy. And Andy came and told me that no matter what I do in graphics, Andy can do it the following year, same performance in the next generation CPU. And at that point, we had really figured out that we were scaling, like all the other people that you have mentioned or presented today. We had figured out that we were going to scale our performance at the rate of basically how many transistors were actually inside a chip. And the CPU could really only scale at the clock speed. And so we were on a different trajectory. Instead of a linear one, we were basically on a logarithmic one. And also, just to finish up the GX, and I'll say why this transitioned over to NVIDIA. I may have misled you, John, about what function was in what chip, because we talked about basically quadrilateral texture mapping. And I went back and I looked at the GX, and I thought I told you at one point that the GX had it. And it turns out the GX actually did every single textile brute force. It actually transformed every single one of the coordinates and rendered it on the screen. And that's why you sort of see the blocky sort of patterns. But on the Nvidia, when we started, so we basically were half pushed out of Sun and actually half pulled out because the PC market was really, really, really big. So we joined forces with Jensen Huang, who was working at LSI Logic, and he was the person in charge of giving Sun all their chips and figuring out how to tape them out and troubleshooting things and figuring out technology. I mean, he was just phenomenal at it. And actually, I found out from him years later that he stole my adder that I put in the TEC and actually put it in the address path of the first RISC chip because they could not make cycle time. But it was like a lot of stuff just going back and forth. Jensen, Chris, and I became great friends as well as our families. And so then what we did
Curtis,
was,
excuse me, just a second to interrupt here. For just not everybody might be as familiar with the story as we are. Is that Curtis and Jensen then started Nvidia, and so that's where we're going in this story, and that's the reason we're talking about quadrilaterals.
right. So a bunch of the stories are true that you hear about us meeting at Denny's and actually trying to figure this out. Jensen was trying to figure out if he actually wanted to do it. A lot of it had to do with his wife, Lori, and Chris's wife, Melody, who basically didn't want to do it, but I jumped ship first in December of 1992. And Jensen had to convince himself he would only join us if we could prove that his company would actually sell at least $50 million a year. Okay, so it's exceeded his expectations, and he's grown into the position of actually, handling a company that is, just so big. So the first thing we did was we took the GX processor, and I built the VL bus back in the day. So I built a VL bus to S bus converter, and we stuck this inside a PC, and we took it on the roadshow for venture capital. And also we started software development on it. So we ported Windows to it, and it actually crushed every single benchmark. So this is like, 4-year-old technology being put into a PC and beating every single thing that was on the market in the PC world. So that gave us basically the courage to just go for broke. So the very first board we did was actually called the NV1. And so this is the board, and the chips were done by SGS Thompson. This is basically the extension board or game port. And it not only had graphics on it, but it also had audio on it, and it had game ports on it. And so, and if you look at the game ports, you'll see that the logo Sega is actually on it, which is a part of our ongoing story. But what I was told moving into the PC market was we had to build a chip that was the same price as a VGA. And we could add a few little things to it, like a 2D, line rendering algorithm. And it's like, well, I wanted to go do a flight simulator, in the PC market. So it's like, how do you go do that? And so what we ended up doing was we had to get rid of the TEC. So there was no transformations on the very first chip. And we basically did, it's a surface, it's a curved surface, which is a quadrilateral, and it had 9 control points. And you can actually do that if your textures are binary in size. You can actually do that with an adder and a shift register. And so we basically sort of duplicated the FBC functionality in NV1. And so it did roaring blitz and basic, rendering. And then it also had these adders that actually would allow you to actually render texture map curved surfaces. And so it turns out, because of a lot of different things, including that there was no graphics language in the PC world, the NV1 board was actually not a big success. But I'll get back to it in a little bit on why it actually was so important to NVIDIA and actually the GPU market. So then it's not well documented, NV2 in the market, because they just never saw the light of day, which was true. But NV2 was actually a product that was requested by Sega. And the code name was Mutara, as in the Mutara Nebula. And if you know Star Trek, that's where the Genesis project happened. So this was actually the follow-on to the Genesis game box. And so NVIDIA's first game box was actually NV2 for Sega. It was not the Xbox, and it was not PlayStation 3. And so I just want to sort of set the record straight for the industry, but it had more features, like it had color compression for the textures and other things. So because all the game stuff was actually in ROMs and still is for Nintendo, but nobody was switching over to CDs because you didn't have a CD player in your PC. And that one, we actually had a Hitachi CPU. So it was basically this board with color compression and a Hitachi CPU on it. And because of some artifacts on the quadratic texture mapping, which we called heaving, when it got very close to the user in clip planes, basically you get huge distortions. And the CPU would actually be doing the transformations, and it was very, very hard to clip these things. Where with respect to the GX, the TEC would actually identify if a triangle or if a quad was actually clipped. And then it would kick back to software. So you could draw it with two triangles, or you could basically draw it in software, which actually rarely happened if you basically did hidden object removal. So then along came, and so basically we showed it in the lab for Sega. Sega ported like Panzer Dragon and Virtual Fighter to the NV1 Edge 3D, the Diamond Edge 3D. They ported it to the game box, and then this was when NVIDIA was going out of business, and we laid off half our employees. They gave us the payment of $1 million. So NV2 actually saved NVIDIA from actually going out of business. So what were the lessons learned on NV1 and NV2 that led to NV3, which was the Riva 128? And so what we learned was we could not compete with the VGA, and we could not compete with 3DFX, which was a board level true 3D company, but very expensive. And so I went back to relook at the equations, and I basically figured out how to do it where we could actually do one divide per cycle, and then you multiply it by like your XYZ, all your lighting. And so that one had sort of 11 engines in it. And I went to Jensen. So this is a side story that I keep telling John of the instant that the GPU was created. I went to Jensen and said, for $35, I can produce a 3D correct graphics card or chip where it's all built into one. And he didn't say yes or no. He said, give me a second. So he went off for a day or two. And over in Terrace Way, we met up in the hallway. And he said, I looked at the timeframes and the new technology and everything, because Jensen's a genius on the fab side because of LSI logic. And he basically said, not only can you build what you want to do in the cost of a VGA, but you're going to have 100,000 gates left over for free, which is 400,000 transistors, which is like the whole GX was going to be free in the corner of the chip. And so with that, we started down this path of cramming as many engines as you can into a chip. So I think that was the mental change for the company and the reinvention of the company. And that led to the Revo 128, the Revo 128 TNT. We basically crammed so much stuff into it that we had, the memory system was too slow. So we upped it from 64 bits to 128. And that's why it's called Revo 128. And it just crushed all the benchmarks. Plus it had, I think it was 5 gigaflops of floating point transformation and 15 giga operations, which had to do with the back end rendering, like, looking up textures and rendering them correctly lit. And so that's where I think the first GPU was, because we had a mental shift about how to go do chips. Then Dan Vivoli, whose salary, he's the marketing guy at Nvidia, came up with this term GPU, which is graphics processing. And I thought it was very arrogant of him to do that, because how dare, this little company take on Intel that has the CPU. And, also his salaries was being paid by the Revo 128 success. But you don't hear much about Revo 128. And as John points out in his book, it's because we modeled it after OpenGL. It was the only language that we really had that had a good 3D pipeline. And it had the raster ops of OpenGL and had the full transform. But nobody in the gaming industry was programming to OpenGL. And at that point, you had the political thing where now DirectX was coming out and Microsoft wanted to kill that.
I'm going to have to interrupt you. I'm sorry.
Okay.
We're gonna run out of our Zoom budget here in a few minutes.
Well, I want to thank everybody. This has been a fascinating discussion, and I've certainly learned a ton. I was always on the other side, actually the artist using these pixels that you guys were spitting to the screen ever faster, and in ever more clever ways. I don't see any questions in the chat room now. All right, so Lou, why don't you just start promoting our attendees here? And
A lot of names I recognize popping up in here.
Hello, Dave.
Hi, Henry.
Wow. And Eric Haynes. Wow. And Samuel Lastra. Oh, should we hold up various boards?
Anybody who's got something to hold up, sure.
Hand wire out.
This one's a TAC board with a whole bunch of functional processors down there and the 200-bit wide instruction storage here.
And we called that an application accelerator, and in modern parlance, that would be a GPU.
This is a VX board, and is the GX that was included on it? I don't exactly remember. That's a Pixel Planes 5 board. This was my first frame buffer. I paid $60 each for 16K DRAMs.
By one.
Yeah, 16K by one.
Those are the good old days, Nick.
Hi, George.
Hi, George.
Hey, Mary.
George was a very early user.
Yeah, that's why his hair's gray.
Yeah.
I lost all mine. Wade, hi, Wade. Ikonas customer number 1.
And again, I want to thank Jon Peddie for the idea and for organizing. Thank you all for attending. We're going to be doing more of these.